very first rules is never use Internet Explorer. Internet Explorer is very reluctant to let you send emails or even process some of the information. So use Chrome, Firefox, whatever, they all work fine. Safari works fine, but Internet Explorer just doesn't work. Sometimes it doesn't work with Blackboard either. So I would not recommend using it ever. Anyway, we're going to look at how to name ionic and molecular compounds. We'll review them just a little bit, just so that we all remember what's going on with them. Then we're going to finish up talking about molecular geometry. Molecular geometry is actually interesting. If you look at this is a covalent compound, molecular compound, and we're just going to look at the rules that allow us to predict what these molecules look like. Because there's differences in what are called electronegativities, and we'll talk about those today too. Geometry is very important because it defines the molecule as having regions in space that are charged relative to others. And that's very important if you want to talk about water, acids, anything like that, solutions in general. So let's go ahead and do this. Before we do, let me just remind you that we have a revised syllabus. Exam number 1 was supposed to be here after chapter 5. I've moved it up here after chapter 4. The reason for that is that chapter 5 has lots and lots of calculations. So does chapter 6 and chapter 7. This is the middle part of the course, and it's very math intensive. The first part is fairly descriptive. The last part is fairly fun. But the middle part has lots of math. So I think it's probably better to cover chapter 5, give you a while to digest it, and then we'll do the exam. So the exam is here. It'll be the 29th. Next week we will have exam 1 review. Now, before exam 1 review, I will give you online, and I will email you one also, a sample exam. Sample exam will look essentially identical to your real exam in terms of the types of questions, but they'll all be different. But they'll look the same, just so you have a feel for what it is. You should work your sample exam as soon as you get it. On this exam 1 review, we will go over every question and answer any questions you may have. Okay? All right, well, as I said, we're going to just quickly review the 2 types of compounds we talked about. Molecular compounds and ionic compounds. Molecular compounds, as we saw when we did Lewis structures, share electrons when they form bonds. As we'll see a little bit later in the lecture, molecular compounds also have a defined geometry. So it's not just a fixed ratio of atoms that make up a compound, but 4 hydrogens in methane are always arranged exactly like this at the 4 corners of the tetrahedron. And we'll understand why in just a bit. Remember that covalent bonds can be single. We also looked at examples of double covalent bonds and triple. So just for every bond we have here, remember there's 2 electrons that are shared. Ionic compounds. We formed ions when we did the Lewis structures last week. We said that we could take an atom and either add an electron or 2, subtract an electron or 2, and that would make an ion. In an ionic compound, the ions, because they're oppositely charged, simply attract each other. They attract each other and pack together in a very specific way. And because of that, they have a very specific geometry. Typically, it's the lowest energy geometry for a given compound. There's one other type of ion. Oh, okay. Well, this is what we talked about. Let's do this. Remember when we made the chloride anion? We took and we added the electrons around chlorine. Chlorine is in group 7. It has 7 valence electrons. To make the chloride anion, all we have to do is add one more electron, and then we have to indicate that this has a negative charge. The role of doing this is that we start off here having electron configuration of group 7. We add one, and we're moving over to group 8, the inert gases. When you have a completed or a full set of electrons, it's very stable. And so that's why these ions do this. Well, there's one other type of ion that we're going to have to know a little bit about. This can be a little bit overwhelming, but let's go ahead and look at them. These are called polyatomic ions. Polyatomic ion is basically a lump of atoms held together by covalent bonds, just like a molecule is, except it'll have a charge. For an example, let's look at strontium sulfate. Strontium is over here in group 2, so it will have a +2 charge. Sulfate consists of 1 sulfur and 4 oxygens. Together they look like this. The sulfate, the bonds here between the sulfur and the oxygen are all covalent. But there are 2 extra electrons in the complex. Because of that, sulfate, SO4, has a charge of -2. Now there are a bunch of polyatomics, a lot of them. Here's the table. For your exam, we're going to limit these to just a few. Just a few that you need to really remember for your exam. And I'll kind of point those out as we go. But this is the table that contains the ones that are of most interest and most commonly used. There's a trick to looking at the nomenclature of a polyatomic and figuring out what it looks like. What you really have to do is to remember what the parent is for a given group. The parent will have a suffix ate. Now we talked about sulfate, right? Sulfate is therefore the parent. It ends in ate. If you take and you add 1 extra oxygen, you get a prefix of per. Keep the 8. That's for 1 more oxygen. If we take 1 oxygen away, we change the suffix to ite. And if we take 2 oxygens away, we change it to a prefix of hypo and keep the ite. But the neat thing about this is that all of these within the same family will have the same charge. So if you can remember what the parent is, you can just kind of look at the name and then add or subtract oxygens to get where you need to go. Let's look at the real examples here. Chlorine is probably the one that works the best with the rule here. The suffix of ate, that goes to chlorate, ClO3, and a -1 charge. Okay? If we add 1 extra oxygen, we do perchlorate, still a -1. If we take one oxygen away, we get chloride. And if we take two away, we get hypochlorite. Now, of the group here, probably the one you want to remember for the exam would be chlorate. So just the parent. Remember, it's ClO3 and a charge of -1. For sulfur, we just did sulfate. If we take one oxygen away, we make sulfite. But sulfate is a nice example of what happens when you add hydrogens to a polyatomic. If we take a hydrogen, H+, and we stick it on sulfate, goes on one of the oxygens, it reduces the charge by 1 because we're adding H+ to it. So this is sulfate with a hydrogen, and our charge is dropped by 1. As far as name goes, we simply call this hydrogen sulfate. This would be sulfite, SO3. Again, we add a hydrogen, charge drops by 1, and we get hydrogen sulfite. The one you want to focus on for the exam is going to be sulfate. So just the parent. For phosphorus, the parent is here, PO3, PO4, with 3 negative charges. Take one oxygen away, we get phosphite, still a -3. But with phosphate and phosphite, we can add 2 hydrogens. Our first one drops our charge by 1. Second one drops it by 2. And we can do that both with phosphate and phosphite. Again, the names would simply be hydrogen phosphate and dihydrogen phosphate, or dihydrogen phosphite. Remember, all of these are covalent. They're molecular. So that's why we use multipliers. Well, I guess we don't know that yet, but you'll figure that out. Carbon. This is carbonate. There is no carbonite. That was in Star Wars. Everyone has heard of bicarbonate. Bicarbonate is actually hydrogen carbonate. So we add hydrogen, drop our charge by 1. We'll talk about acetate when we do acids. I think that's chapter 8. Cyanide is one you probably should remember. Cn-, that's cyanide. Nitrogen, nitrate, NO3, 1 negative. Nitrite, NO2, take one oxygen away, but still -1. Nitrate's the one you want to remember for the exam. And the other one is this guy. This is ammonium. This is the only cation polyatomic that we're going to deal with. Ammonia is in H3, right? We've done that before. If we add an H+ to it, we wind up with an H4 with a plus charge, called ammonium. So this is just a quick overview of them. Again, the ones that you want to focus on are going to be the parents, so nitrate, carbonate. Cyanide is always a nice one. Sulfate, chlorate, whatever. Any questions? All right, let's look and see how in the world we make these polyatomics and put a charge on them, and why they have a charge. Let's do it by using our Lewis structure for something like chlorate. Remember, chlorate is ClO3 with a -1 charge. If we're going to draw the Lewis structure, first we have to find the atoms. Chlorine is here in group 7, and it's going to be in the middle. It's going to have 7 valence electrons, right? It's group 7. Oxygen is here in group 6, and we're going to put 3 oxygens around the chlorine. So we start off with something like this. Our chlorine in the middle here has 2, 4, 6, 7 electrons. Each oxygen has 2, 4, 6 electrons. Now what we want to do, obviously, is make bonds here. As we look at this, we can clearly make a bond here. No problem, except we have 1 extra electron left over. Here, the way they've lined up, we have 3 electrons this base, 3 electrons in this base, 2 singles sitting up here. First thing I would do is kind of rearrange those. Remember, Lewis is just bookkeeping, so we can do that. I'm going to take one of these electrons, just move it up, do the same thing here. So we have only 2 electrons between the 2 atoms. When we do that, we can make a bond. So let's do that. So we move these electrons up. Now, around this oxygen, we could have 2, 4, 6, 8. This oxygen, 8. But here we're missing 1 electron on the chlorine, aren't we? That's why chlorate is a -1 charge. What you do is, remembering it's a -1, we simply need to bring in an electron from somewhere and put it here. When we do this, this whole group of atoms will have a -1 charge. Now, it's trivial to write the structure and make the bonds. We scooch everything close together. Remember, it's all got a -1 charge. All of our oxygens have 2, 4, 6, 8 electrons. Our chlorine in the middle also has 2, 4, 6, 8 electrons. So everybody satisfies the octet rule. Everybody's happy. And the whole complex has a -1 charge. This is how you would draw it with the dashes. Again, these are covalent bonds. And the whole group here simply has a -1 charge.
So the parentheses has to be in there?
Yeah, parenthesis has to be around it in a Lewis like this, so that you can show that the negative charge is on the complex. Now, in reality, the geometry here is planar, and it's trivial. So these 3 things are all in a plane, and the electron is delocalized over the whole thing. So it's truly shared with all the atoms. But this is the way you build it with a Lewis. Now remember, the whole point of putting the electron on there was to satisfy the octet rule. And just to remind us all, the octet rule, once again, if we wind up with 8 electrons in the valence shell, 8 electrons around an atom, that's very stable configuration, just like the noble gases here. Those are inert gases, they don't react. So once you fill up the shell, that's a good thing. That's called, again, the octet rule. However, it's only fair to point out that there are exceptions to the octet rule. We're going to talk about a couple. This is SF4. 1 sulfur, 4 fluorines. The actual molecule looks like this thing here. This geometry, well, is interesting. Before we do the geometry, let's look at just the picture here. We have these 3 for these two fluorines and a lone pair of electrons in an equatorial position. They're equatorial, they're in the equator, so they're around. And the geometry there is trigonal. We have these two fluorines sticking straight up and down. We call those axial. So we have axial and equatorial fluorines. For something like SF4, this particular geometry is called seesaw. Now that just goes to prove that chemists have senses of humor.
Seesaw?
Seesaw. If you look at this structure and turn it on its side, you can imagine it as a little seesaw bouncing up and down. So that's the origin of the name. But let's see how in the world we make something that violates Lewis's rule. Again, let's build it step by step using our Lewis structure. First of all, we have to find sulfur. Sulfur is here in group 6, so it has 6 valence electrons. Fluorine is here in group 7, so it will have 7 valence electrons. Let's start off by putting our sulfur in the middle and 4 fluorines around it. Now, as we look at this structure, again, we can see that we could make a bond here nice and easily, couldn't we? And that would give our fluorine 2, 4, 6, 8. It would be happy. Same thing with this guy, 2, 4, 6, 8. But we have 3 electrons here, 3 electrons here. You can't make a bond with 3 electrons. It has to be 2, only 2. So a simple way to imagine what happens is let's just identify a couple of these electrons and let's get rid of them. Okay, a Lewis structure is bookkeeping. So I'm just going to go and put them over here in the corner. Let's take 2 and just put them down here. We'll call this storage. All right, so we put these electrons down in the corner. Well, remember they're there, but they're just gone right now. But if you look at what we're left with, it is just so simple to make these bonds, isn't it? 1, 2, 3, 4. We scooch them all up, make our bonds, and we have SF4. But, being honest with ourselves, we know that somewhere down here on the floor, we have those 2 extra electrons. So what you have to do is put them back. There we go. And now the sulfur has 2, 4, 6, 8, 10 electrons. This is called valence expansion. If you have an element that's in the 3rd period or below, sulfur's in the 3rd period or below, you can actually cram up to 14 electrons around it. Valence expansion is called. That's one reason that we're only dealing with the first 2 periods, because they're simple. But down here on, you can put up to 14 electrons, not just 8. This is what it looks like again. Now I've put in the extra electron pair, have our axial things. These 3 are equatorial, and again, they're all in the equatorial plane, and the other 2 are straight up. So this is an exception to the octet rule, because instead of 8, we have 10 or more electrons around our central atom. There's one other very simple one. Why don't you hush for a second and you draw a Lewis structure for BH3.
that another exception?
Of course it is. Boron is here in our third group, so it'll have 3 valence electrons, right? Hydrogen is in the first group, and it will have 1. Our boron goes in the middle with its 3 electrons, and we put 3 little hydrogens around it. What we wind up with is this. There's our boron, 3 electrons, and there's our 3 hydrogens. All right, as we look at this, yeah, we can do this. We can make 1, 2, 3 covalent bonds, no problem. Scooch them up. But if you count up, this poor boron only has 6 electrons. Each hydrogen has 2, like it's supposed to, just like helium up here. Goes from hydrogen to helium. But the boron is stuck with only 6. And there's nothing we can do about it, is there? There are no other electrons around that we can mess with to give this poor guy more electrons. This is an example of a compound where we have too few electrons. When you get a little more advanced into chemistry, you'll see that this is called a Lewis acid. Lewis acid is an electron acceptor. Basically, this poor boron is electron deficient, and it dearly wants more electrons. It will essentially borrow electrons from anything in order to give it its full 8.
Did you just say deceptor, an electron deceptor or acceptor?
I'm sorry,
What did you just say? The Lewis acid was?
it's a Lewis acid. It's an electron acceptor.
Acceptor.
Right. So we put something with extra electrons, unshared pair or whatever. They will stick here and attach themselves to the boron so that boron has its full 8. We'll talk about that in more detail if you get to intro on general chemistry. Any questions on the concept? So we had 2 exceptions to the Lewis octet rule. Again, you can put more electrons around if you're below the 3rd period. Or, in strange cases, you can have too few electrons and be left with a Lewis acid. All right. Let's go and talk about naming these compounds. Let's do ionic compounds first. When we looked at this, I referred to this as the sodium cation, sodium plus, and the chloride anion. We said that these things are held together by electrostatic attraction because we have a plus and a minus. They pack together in a very particular way, and that's why crystals, where we have lots and lots of these arrays, have very particular shapes. What we want to look at here is the ions themselves, how you know what charge is going to be on an ion. And then we're going to figure out how we came up with these names, chloride, whatever. If you have an ionic compound, you can predict the charge that it will have simply by looking at its group number. Let's start over here with things in the first group. If you have an element that's in the first group here, one of these blue guys, metals, that's going to be a +1. The second group is going to be a +2. The third group, these will all be +3. And the fourth group, they will be +4. Very, very simple. Now remember what we did with sodium. Sodium was here, it lost an electron. That made it +1. Over here, magnesium will lose 2 electrons. Aluminum will lose 3 electrons, etc. Once you get past group 4, things change. Remember we said chlorine was going to gain an electron and be -1. Sulfur was going to gain 2. Nitrogen gained 3. So starting at group 5, we go -3, -2, and -1. So the breaking point here is between 4 and 5. We go from positive on this side to negative on this side. Of course, group 8, they're the inert gases. They don't form ions, they don't do anything. They just sit there. So step 1, if I asked you what kind of an ion aluminum would form, all in the world you have to do is to look at the periodic table, say aluminum is here in group 3, it's a +3 cation. Cation. Charged, a positively charged ion is called a cation. Negatively charged is called an anion. That's in there. Cation, right. All right, so we've made these ions. We know how to look at a metal and figure out if it's going to be, or what charge it's going to have, simply by looking at the. Next, let's look at what's called the principle of charge balance. And this is really quite intuitive. If you're going to make a compound, the compound needs to be neutral. It can't have a charge, net charge overall. So you have to have the same number of positives as you do negatives. Again, this is called the principle of charge balance. If we had an ionic compound made up with magnesium and sulfur, we would look at our periodic table. Magnesium is group 2, so it's a +2 ion. Sulfur is over here in group 6. It's going to pick up 2 electrons and be a -2. The compound made from these two would have a +2 and a -2, and the net charge would be 0. Sodium and bromine, same thing. Sodium we're in group 1, so that's a +1. Bromine we're in group 7, that's a -1. They go together 1 by 1, so our compound has a net charge of 0. If we paired up sodium and sulfur, because sulfur is a group 6 with -2, we need 2 sodiums to do that, don't we? So we have 2 +1s, 1 -2, but we're still 0. Magnesium and bromine, same thing. Bromide is going to be -1. Magnesium, because it's group 2, is +2. So we need 2 of these guys to balance it, again, to make it 0. The bottom line to take care of, to remember here, is that you need to adjust the numbers of positives and negatives so they always wind up 0. All right, once you know how to do that, you're ready to write the formula. Really, the only rule to remember in writing the formula is that you need the simplest whole number ratio. the simplest whole number ratio. For magnesium and sulfur, that would be 1 to 1. And we would simply write it as MgS. 1 and 1. If we said that, well, we could still balance this out at Mg2S2, and you could, but that would be wrong because you use the lowest whole number ratio. For sodium and bromine, 1 positive, 1 negative, NABR. Now again, when we have multiples, we have to show we have 2 sodiums for every sulfur. So we use our subscript, 2 sodiums to every sulfur. Same thing here, 2 bromines for every magnesium. Lowest whole number ratio. Any questions? Let's work backwards. If I say we have NaCl, that should tell you we have 1 sodium and 1 chlorine. If I told you we had HF, that would tell you 1 hydrogen and 1 fluorine. H2O, 2 hydrogens for every oxygen. And let's look at our polyatomic here. This is sulfate, remember. Sulfate has a -2. So we need 2 potassiums, that's a +1, over here in group 1. Bonds, this is a -2. Taking this formula apart, we have 2 potassiums, 1 sulfur, and 4 oxygens. Make sure you know how to look at a formula and simply dissect it into the proper number of atoms. That's a standard sort of test question. Any questions? All right, let's make some compounds then. Go ahead and write me a compound made up of magnesium and chlorine. Step 1, you want to look at your periodic table and find them. Magnesium is here in group 2. So what will its charge be? +2. Chlorine is over here in group 7. So it will gain 1 electron and be -1. So we have a +2 and a -1. To get neutral, what do we need? We need 2 chlorines to every magnesium. And how would you write that? You would write Mg for your magnesium, and then Cl with the subscript 2 for chlorine. 1 magnesium and 2 chlorines. Now, the only time this exercise gets the least bit confusing, I think, is if you have something like aluminum and oxygen. Go ahead, look at your periodic table and ask yourself, what's going to be our charge on aluminum? Basically, what group is it in? It's in 3, so it will be what? A +3. Oxygen is here in group 6. It needs 2 more electrons to move over to the ion, so it will be a -2. Yeah?
What does oxygen have anything to do with neon?
I'm sorry?
What does oxygen have anything to do with neon?
With,
What does aluminum and oxygen have anything to do with neon?
oh, oxygen. Remember, This we start off with 6 valence electrons. It wants to pick up 2 more. So it has the same octet that neon does. Remember, with
So
neon,
the same thing applies for carbon?
carbon will tend to go this way. Remember, the break is here between 4 and 5.
So the same would be for nitrogen?
Yeah.
With one go because of the negative and positive.
Right, because you want to gain the electrons to get over here so you look just like group H. All right, so aluminum is +3. Oxygen is -2. What you have to do is come up with a ratio that's going to make this neutral. Now, you know, this really isn't rocket science, but there's a very simple little symmetry rule that you can use. This just makes this easy as breathing. What you do is just simply look at your 2 ions, okay? We have aluminum with a +3, oxygen with a -2. As you write your compound, just simply take your 2 elements and then look at the charge on the opposite one. Aluminum is a +3. That means we're going to need 3 oxygens. Oxygen is a -2. That means we're going to need 2 aluminums. Now think about this. Every aluminum is +3, right? So this is 6 positives. Every oxygen is -2. This is 6 negatives. So a simple little symmetry crossover, and it works every time. Look at the charges, swap them one for the other. Now there is one danger to this that we'll look at right now. Do beryllium and selenium. Beryllium. Symbol is Be. It's in our second group, isn't it? So what will the charge be? +2. Selenium is here underneath sulfur and oxygen, so it's group 6. It's going to want to pick up 2 electrons, isn't it? So it's going to be a -2. So what we have is a +2 and a -2. So let's say that we were playing a little symmetry crossover game, and we simply wrote them. All right, what would we do? Well, there's a 2 here and a 2 here, so you could write it that way. But that'd be wrong, wouldn't it? Because remember, the other rule is not just neutrality, but the lowest whole number ratio. So even though the crossover works, we have to change this to be ES, 1 and 1. But aside from that, the crossover rule is real simple. If you have complicated ions, complicated compound, that can make it really simple to do. Just remember the crossover, but always remember lowest whole number ratio.
Well, wouldn't you just cross those out since they were 2 plus 2 negative?
Right. All right. As we have been going through these things, I've been slipping up every now and then and calling one chloride and bromide and stuff like that. How that is the nomenclature for simple ionic compounds. And let's see how that goes together. Remember, the ionic compound consists of a cation, that's the positive, and the anion, that's the negative guy. Right? When you go to name these things, the cation always comes first. And the cation is simply the name of the element. So if our element was magnesium, our cation was magnesium, first word would simply be magnesium. Separate word all by itself. The second word, the name of the anion, what you do is you look at the element and you say, okay, what's the root? You define yourself what the root is. Just take the root and add IDE. Multipliers, you don't stick in multipliers to tell you how many you have. All you do is take the root and add IDE. So, here we have a compound with magnesium and bromine. Our first word is simply going to be magnesium. Our second word, well, we look at bromine and we say, what's the root? Well, it's brome. Brome, B-R-O-M. So all we do is take brome and we add IDE. And this is magnesium bromide. You don't need to say anything about the fact that there are two of them. Why? Because you're just supposed to know that. You're supposed to know that magnesium is in group 2, it's a +2. So we need 2 bromines to balance it. Our next one here, sodium and chlorine. Our first word is going to be sodium. The root for chlorine is going to be chlor. And all we do is add IDE. Potassium and sulfur. Our first word is potassium. The root for sulfur is going to be sulf. And all we do is add IDE. DE is beryllium, isn't it? Our first word is simply beryllium. We know that bromine, just like up here, is going to be simply bromide. And that's all in the world there is to naming these things. You don't have to worry about multipliers at all. Any questions? Well, go ahead and name these guys then. Ca is calcium, isn't it? So that's our first word. Bromine, root is brome, add an IDE. You simply have to call it calcium bromide. Aluminum. First word is simply aluminum. This is oxygen. What do you think the root's going to be? Ox. And we're going to add an IDE. Li is lithium. This is sulfur. What's our root? Sulfur. So this is simply lithium sulfide. We've already done Ca. What is it? Calcium. We've done oxygen. So what is it? Calcium oxide. Now this is an interesting one. This is nickel and chlorine. You look at the periodic table, find nickel. It's here in the middle. It's a transition metal. But still, we're going to name it more or less the same. We're going to say we have nickel, we have chlorines, so it's going to be a nickel chloride. However, we will see in just a little bit that because nickel's a transition metal, knowing its charge is not always evident. And so the proper name for this is actually going to be nickel 2 chloride, where the 2 tells us that nickel has a +2 charge. And that's, getting ahead of myself a little bit. That's because transition metals, these guys in the middle, can quite often have different charges. 1, 2, 3, 4, whatever. So that's why for these, we're going to have to say what the charge is. But we'll do that in a little bit.
You're gonna have that in the test, that nickel too?
What, on the exam?
Yeah.
Oh, you'll have something.
No, I mean, for the middle transition.
Yeah, well, you'll see, you'll see.
Oh, no.
All right, now the problem with ionic compounds isn't going forward. It's going backward. Where you're given the name and you have to write the compound. So, look at your periodic table, ask what the charge is on the cation, what the charge is going to be on the anion, and what ratio you need. Calcium is in what group? It's group 2, so it's a +2, isn't it? Nitrogen is way over here in 5. It's going to be an anion. What's its charge going to be? It's going to want to pick up, because it's in 5, it's going to want to pick up 1, 2, 3 electrons. So it's going to be a -3. So what we're dealing with here, let's be real old-fashioned. Calcium +2 and a nitrogen -3, right? So use your crossover. Yeah, -3 up here, that means you need 3 calciums, +2 here, 2 nitrogens. And I got it right. All right, do magnesium oxide.
Hang on one second.
Yeah.
The calcium, since it's in
2.
3 and 4, then you just gotta go that way 1, right? So you can take 1 charge away to get to the 3 charge.
So we're going to take 2 electrons away. It's actually going to go all the way back to positive.
So then why is it 3? Why does it say C 3 and 2?
Nitrogen, that's nitrogen here. Nitrogen, remember we're passing through 4, so nitrogen is going to pick up 1, 2, 3 electrons. It only has 5 electrons, needs 8.
So then why does the
On this end of the periodic table, energetically, it's more favorable to lose electrons. This end is more favorable to gain electrons. All that has to do with energy balance.
So again, why is it Ca3 and N2, not Ca2?
That's when you crisscross them.
He swapped it.
Yep, if you can read that there. Remember our crossover, this is calcium plus 2. So the 2 is going to come down here, 3 is going to come down here, Ca3 and 2.
This happens for each one. This happens for each one. This happens.
Oh, this is, well, you know, this really doesn't have anything to do with the actual movement of electrons. This is just a very simple little symmetry tool.
Does it happen every time?
Oh, yeah. Yep.
You can cross over every time?
Yeah, unless you wind up with, 2 and 2, and then you have to reduce it to 1 to 1, like we did with beryllium. Our next guy, magnesium. Magnesium is in group 2, isn't it? So it's a plus 2. Oxygen is in group 6. What is it? It's a minus 2. So we have 1 magnesium, 1 oxygen, and it's just MgO. Lithium is in group 1. What's it going to be? Plus 1. Iodide is here in group 7. Needs 1 more electron. So it's going to be minus 1. Plus 1, minus 1. Pair them up. Lithium iodide. You seem to be having trouble with the anions here.
Yeah, I don't get it. So MgO, right? So Mg is in the third period.
Right.
So it's
So
going to go left, correct?
okay, it's going to lose 2 electrons.
It's going to lose 2. Why does it lose 2?
Why does it lose 2?
Why does it lose 2?
Well, again, it's all energetics,
So there's only one other group left on the left-hand side.
right? But what happens is it wraps around. Remember, it's trying to get down to the core 8. So if it loses 1, it's down to sodium. If it loses 1 more, it's all the way up here to neon. It wraps around. Neon has 8. So by losing 2, it's up here at neon.
Why is it trying to lose? Why is it trying to get to neon if it's before the fourth?
On what, on this side of the table?
Yeah.
Energetically, these guys lose electrons. It's more energetically favorable for them to lose and for these guys to gain.
So all elements want to be in a which
That all elements eventually want to wind up looking like group 8.
no matter
These
where-
guys do it by losing. These guys do it by gaining.
Okay, so oxygen having 2 to the right, why does it not have any?
I mean, you could say, okay, oxygen could lose 6 electrons, go all the way around here to helium.
No, because you want to gain 2 to get to neon, correct?
Right.
So then why would the charge be Mg2O2?
Because remember, we want the lowest full number ratio. So the 2's have to go down, they cancel out, it's just NgO. Lowest full. And the same thing with lithium iodide. Barium. Barium is a second period, right here. So what's its charge? Plus 2. Phosphorus is sitting over here in group 5. So it's going to pick up how many electrons? 1, 2, 3. So phosphorus will be a minus 3. We have a plus 2 and a minus 3. What's the ratio? Use your crossover. just like calcium nitride, exactly the same. We're going to need 3 of the bariums and 2 of the phosphorus. This gives us 6 positives and 6 negatives. And finally, beryllium fluoride. What group is beryllium in? Number 2. What's its charge? +2. Fluorine is over here in group 7. How many electrons does it want? It's in 7, it wants 1 more. So it's a -1.
So it goes -3, -2, -1?
Mm-hmm. So here we have +2 and -1. So we need 2 fluorines to balance out the beryllium, Be at Be2. +2 and 2 -1s. Remember, you split at group 4. These are going to lose electrons, these are going to gain. All right, remember, we just did polyatomics.
Split at group 4 or group 5?
What's that? Split in between 4 and 5.
So really 5.
Yeah. At 5, we start picking up electrons. All right, remember our polyatomics. If you want to name something with a polyatomic, all you really have to do is, once again, just put the cation and then the name of the polyatomic. That's all. CaCO3. You can look at your table and look up CO3. And what is that? This one you should probably know. It's carbonate. So if we were to name this, we would simply put the cation, calcium, and then we would write carbonate. Calcium carbonate, that's marble, chalk. Basically, it's rock. Remember I said we had one polyatomic that had a positive charge that you should probably remember. And that was an H4, and that's ammonium. Yeah.
Sorry to interrupt, but why would you call it, the ID instead of why would you call it calcium carbonate instead of calcium carbonate?
Oh, well, first of all, there is no carbonate. Carbonate, just by definition, the definition of the carbon polyatomic, that's the parent, CO3. Right? Sulfate is SO4. That's just what it is. That's just the definition of the parent. And from the parent, you either add or subtract. And with carbon, there you don't form a carbonate.
So then how come over here aluminum O3 it says aluminum oxide? And then over here it says CaCO, right? It's got oxygen in it. So why would it be calcium carbonate if it's oxygen?
Well, remember the polyatomic is different because it's a covalent bond. There's a covalent bond, and they go together as a group. So we have one calcium, one carbonate. Carbonate is a group, doesn't change. NH4 we said was ammonium. We know for chlorine, we say our root is chlor, so that's going to be chloride. And we would simply call it ammonium chloride. Here our polyatomic is what? SO4. One you should know. Sulfate, right. Sulfate, carbonate, kind of know the parents. Our cation is simply sodium, so we write that. And then we write the name of the polyatomic, sodium sulfate. Now, if sulfate is the parent, and we take one oxygen away, what do we get? Sulfite. But the charge stays the same, doesn't it? Here our cation is just lithium, so we write that. And then for our polyatomic, we would just write sulfite.
Alright, so sulfate and sulfite, what are the differences? It's talking about a charge here. Is there a certain amount of charge that constitute what you call fate and light?
No, it has to do with the number of oxygens. SO4 is defined as the parent, and it's defined as having one sulfur, 4 oxygens. Take one oxygen away, we change the name to sulfite. One sulfur, 3
So
oxygens.
it needs to have 4 oxygens in order to be called a fate.
Sulfate, right? 3 oxygens would be
Anything less than
sulfite.
4 would be sulfite.
Well, one less would be sulfite.
What if it was Li2SO2? It wouldn't do that, would it?
That doesn't exist. And finally here, our polyatomic parent here for PO4 is what? That's phosphate. PO4 is phosphate. A cation is potassium, that's simple. The only thing that's different here is we stuck a hydrogen in the middle, didn't we? So we need all 3 in our name. We need potassium, hydrogen, and phosphate.
Could you call it potassium hydrophosphate?
Nope, because it's called potassium, hydrogen, phosphate. Yeah.
Alright, one more question about this SO3, this third oxygen, third charge oxygen. You have example D, lithium sulfate, sulfite, with the third oxygen charge. And then you have example A, calcium carbonate. Why is having the oxygen charge still included? Why would it be called carbonate instead of carbonate? Is it just because of the name?
The way they define the parent, the polyatomic parents, has to do with the organization of the oxygens around the central element. Carbonate, 1 carbon, 3 oxygens. That's your standard that you begin with. Sulfate, your standard is 1 sulfur, 4 oxygens. Phosphate, 1 phosphorus, 4 oxygens. So those are just referred to as the parents.
The name of the element.
Again, it's a covalent lump. No, it's a lump. It's a single entity. It's like the water bottle.
So if I have an exam and I get lithium, if I go Li2CO3 and I call it lithium carbonate, do I get it wrong?
CO2?
No, CO3. If I go
No, like two.
Li2CO3,
That would be lithium carbonate. So let's do them backwards here. We can skip our first one because we didn't cover this on our slide. Permanganate is MnO4. Minus
I was
1
trying
charge.
to figure it out.
Yeah, we didn't cover this one. So that's what that would be. Now, potassium permanganate is an interesting compound. It's used in water purification and stuff like that. if you have a well with dirty well water, they'll put an injector on there that puts a little bit of purple potassium permanganate in there to kill things, etc. Doesn't kill you so fast, but works well with bugs. Barium sulfite. Now, we know for sulfur, our parent is SO4, right? Remember that.
This is SO3.
So this is SO3. The charge on that is going to be -2, right? Because all the sulfurs are going to be -2. Sulfite and sulfate. Barium is here in group 2. So what's its charge? +2. So we have a +2, we have sulfite, which is -2, and we simply write them like this. Chlorate. Chlorate is one you should know as well. You don't know the parents, that's all. Chlorate is ClO3, and it has a -1 charge. All right, aluminum. Where's aluminum? What's its charge going to be? +3. It's in group 3. So, if every chlorate is -1, how many chlorates do we need to make it neutral? We need the same number of positives and negatives. So, aluminum and 3 chlorates. Now here's where you have to be careful. The way you write this is like this. Remember, I keep saying that chlorate is a lump. It's a single entity. And what this tells us is that we have 3 of these single entities paired up with our aluminum.
Is that an L or
That's a
an
Cl.
I?
Cl. So each of these is a -1, and we have 3 of them. The aluminum is +3. All these together are -3. Nitrate. Nitrate is the parent for nitrogen, right? Nitrate is NO3, and it's a -1. Now silver, by George, is one of these transition metals. So you could say, hey, how do you even know what the charge is? Well, because it's silver. Silver is almost always, 99.997% of the time, will be +1. That's just one you could just remember. So if this is +1 and nitrate is -1, our formula would look like that. Now barium cyanide. Cyanide, that's one I said you should probably remember. Cn-, -1. 1 carbon, 1 nitrogen, -1 charge. Where's barium? It's here in group 2. So it's what? +2. How many cyanides do we need? If they're each -1, we need 2 of them. How do we show that? Again, we have to put it in parentheses. If we didn't have our parenthesis there, it would look like CN2, wouldn't it? And that would be wrong. So this again tells us that the cyanide is just there as a lump.
So wait, the cyanide, you have 2 capitals, CNN. Is it,
That's 1 carbon, 1 nitrogen with a negative charge.
am I supposed to know that that is cyanide?
Well, because you look at your table and you say, oh, I remember. Cn minus is cyanide. Oh, I remember that.
Yeah, now I do, but like I didn't know before.
No, see, you learned something. All right, well, let's show how smart we are.
Now I feel.
Name these compounds for me.
Wow, it looks like a placebo.
PB, what's PB? PB is lead, right? So we have a lead and an oxygen. What are you going to call it? Lead. And the root is ox, so it's going to be lead oxide.
Wait,
Again, that's why
you
you
gotta
need.
study that chart.
All right, how about this guy?
So that one is
P-
lead oxate.
It's
The
lead
same.
oxide too, isn't it?
Why?
Because we don't use multipliers, remember?
Oh,
This next one is iron, isn't it? And oxygen. What would you call that? Well, iron oxide. And our next one is iron oxide, and so is the next one. Obviously, we have a problem. Remember when I said about nickel being a transition metal and them having different charges? Well, lead and iron are examples of transition metals. For these guys, we have to define what we call their oxidation number. Now, this is a fancy word. The oxidation number simply compares the element, as it's in your compound, to the element in the periodic table. So, here we're comparing lead, number of electrons around lead, to lead in the compound. Same thing with iron. Iron in the compound relative to iron in the periodic table. Now, the concept here is really, really simple. Let's say we're looking at magnesium bromide. The oxidation number for these simple compounds is going to be the same as their charge. So magnesium is a group 2 element. It's going to have a +2 charge. Bromine is group 7 over here. It's going to have a -1. So if we use that terminology, because magnesium is a +2, bromine is a -1, we could also just say that the oxidation number of magnesium is +2, oxidation number of bromine is -1. It's just a different way to describe the charge. Instead of saying charge, we call it oxidation number. For lithium phosphide, lithium is group 1, so it's a +1. Phosphorus is over here in 5, so it's a -3.
so did you just reverse the numbers? Because I see the 3 on over here.
So the oxidation number of lithium is +1, and phosphorus is -3. It's just a different way to say the charge. Now, if you go on in chemistry, you will use the concept of oxidation number differently. And there are rules for how you use it. This is the set of rules, but as far as we're concerned, only part of this rule that you need to remember is going to be here, oxygen is always -2, and halogens, so that's anything in group 7, is going to be -1. Those are the 2 rules you need to remember. Oxygen is +2, halogens are -1.
say were hydrogen?
All the ones in group 7. All right, let's see how this works then. Here's our 2 lead oxides. What's the oxidation number for lead in these compounds? All you do is you look and you say, okay, we have an oxygen. What does the rule say? Oxygen is going to be -2. Now, if this is neutral, what's the charge on the lead? The lead has to be +2. In this guy, we have an oxygen, right? We have 2 of them. Each one of these is going to be a -2. So how many negatives do we have? 4. Therefore, the charge on the lead must be +4. And that makes it neutral.
And how would you write that?
Well, we'll get to that in just a second. Let's do a couple irons. We've talked about sulfate, right? What's the charge on sulfate? Sulfate is -2, right? We know sulfate is always going to be -2. If this is neutral then, what's the charge on our iron? +2. Here we have 3 oxygens. What's the charge on the oxygen going to be? They're each going to be a -2. So how many negatives do we have? 6 negatives. Now we have 6 negatives. We have to make this neutral. We have 2 irons. So what's the charge on the iron? It has to be a +3. That will give us 3 times 2, 6 positives. 3 times 2, 6 negatives. Now, how do you write it? Just like we did with nickel. What you're going to do once you figure out what the charge is, you just put the charge in parentheses after the cation. That's all you have to do. So, we said in this guy, we had 4 negatives. So the lead had to be +4. We would write this as lead 4 oxide. No space, in parentheses. We said in this compound, if the oxygen was -2, the lead would have to be +2. So we would write it, lead 2 oxide. What's our charge on carbonate? Carbonate. It's your table. Carbonate is -2, right? We have 1 carbonate and 1 iron. If the carbonate is -2, what's the charge on the iron? It has to be a +2. So we will call this iron 2 carbonate. Every halogen, bromine is a halogen, is a -1. We have 3 minuses here. So what's the charge on the iron? It's got to be iron 3 bromide. Now I'm sure all of you want to run and practice this. Fortunately, there are tutorials for this. What you do for this guy, binary ionic, naming ionic, I think is what it's called. You just look at this and you write the name. So, what's our first word? Barium. This is iodine, isn't it? We don't use multipliers, so it's simply barium iodide. Yeah. Barium is +2.
Right, but it isn't AL.
It's barium is BA.
B8. Here's another one. Copper and iodine. Where's copper? It's a transition metal, isn't it? So we have to show the charge. What's the charge on an iodide? -1. So the charge on the copper must be +1.
So just Roman numeral 1.
Copper 1 iodide. See how simple that is?
I have a question.
Yeah.
If you can go back to that. So the only time we use the Roman numeral in the compound would be when it doesn't have any exponential.
Right, if it's one of the transition metals. So anything from after 2 and before 3, all of these guys, the transition metals, you need a charge. ClO. One you probably don't remember, that's hypochlorite.
Did you skip one?
I don't think so.
I have CUL as the next one.
Oh, yeah?
That's what we just did. Is that for 1 iron?
CUI, right. We did that.
CUI.
So, hypochlorite is a -1 polyatomic. So we have 3 negative charges here. What's the charge on the iron? We have 3 negatives, we need 3 positives. So we'll call this iron 3 hypochlorite.
Why'd you call it a hypo?
Well, that's the name of the polyatomic. You start with, you look back at your table, chlorate had 3 oxygens, chloride has 2, hypochlorite has 1. Sodium hypochlorite is 4 oxygens.
So you have CL, which is a chloride, and
ClO.
then oxygen.
We have 3 of them. Because of each -1. Each ClO is -1. So we need 3 positives from the iron to balance out our 3 negatives here. Yeah.
So we just got done, since it's a transition, it's gonna be happening. Iron is a transition, it's gonna happen.
But it's
So it doesn't matter whether it has an exponent or a charge or not.
Nope.
In the name. It's just whether it's a transmission.
unless, of course, we're dealing with molecular compounds. Now, molecular compounds are very, very similar naming, except that here we're going to use multipliers. Okay? Multipliers. 1 is mono, 2 is di, 3 is tri, tetra, penta, hexa, hepta, whatever. And all we're going to do is insert the multiplier into the name. So let's see how simple this is. Here we have 1 carbon and 4 chlorines. How would you name this guy? Well, there's 1 carbon, but there's a rule. For the first element same. If there's only one of them, you don't use mono. If it's a second element and there's only one, that's when you use mono. So our first word simply going to be our carbon, and we don't put mono in there. Now, right, we have 4 chlorines, right? So this is going to be a chloride. And what was the multiplier for 4? Tetra. Mono, di, tri, tetra. Therefore, this is tetrachloride, all one word. That's simple.
That's
One sulfur, 2 oxygens. What's our first word?
sulfur.
Just sulfur, that's it. No mono, just sulfur. We have oxygen, so it's an oxide. How many do we have?
Dioxide.
2. This is sulfur dioxide.
The second word is always going to be all lowercase.
No,
No?
doesn't matter. Upper or lower, doesn't matter. All right, here we have 2 nitrogens and 1 oxygen. So we need to use di for our first element, don't we? So we'll simply call this dinitrogen. Now there's only 1 oxygen. This is where you use the mono. Dinitrogen monoxide. We drop out the second O because that would be too many. Now if this was on an exam and you put in the second O, I wouldn't care. I'd be thrilled if you got it. How about this one? 2 nitrogens and 5 oxygens. Well, we know what we do with 2 nitrogens, right? That's a dinitrogen. And what's our multiplier for 5? Pent. Penta, yeah. But again, we have an oxide, so we kind of drop the A on the end, because that would be AO, that would be stupid.
So when you start with
Yeah, when you got 2 strange vowels together, you get rid of one. All right, let's go ahead and do the list. One carbon, 2 oxygen. What's our first word? Carbon. 2 oxygens is a dioxide. We have 2 hydrogens, so it's a dihydrogen. Only 1 sulfur, so we need to put a mono in there. One silicon. Don't need to worry about the mono, we just write silicon. For hydrogen, we're going to use hydride. Okay? So this is silicon, our multiplier for 4, tetrahydride. One sulfur, 3 oxygens. First word is sulfur. 3 is a trioxide. One nitrogen, 3 chlorines. First word is nitrogen. Trichloride. Now, some of these can get fun. But they're so delightfully predictable. Tetra, right? Tetraphosphorus. 6 is hexa. Tetraphosphorus hexasulfide. 2 iodines, that's a diiodine. 7 oxygens would be a heptaoxide.
So how come you didn't remove that other ion? And how you did? Ionic.
Oh, I didn't, you need the full name of the element.
Oh, yeah?
So, even though there's 2 i's. 1 oxygen, so our first word is just oxygen. 2 fluorines, so we have a dichloride. 1 carbon, so our first word is carbon. We have 4 hydrogens, so this is a tetrahydride. This is methane, natural gas. And finally, 4 sulfurs. What's that going to be? Tetra, sulfur. 2 nitrogens, dinitride. Now where this really gets easy is when you go backwards. Remember for ionic compounds you had to think to go backwards? Here you don't have to think, because the ratio is given to you. Isn't that convenient? Nitrogen triiodide. 1 nitrogen, 3 iodines. Diphosphorus pentoxide. 2 phosphorus, 5 oxygens. Sulfur trichloride. 1 sulfur and 3 chlorines. Nitrogen monoxide. 1 nitrogen and 1 oxygen. This is just no. Hydrogen monochloride, 1 hydrogen, 1 chlorine.
What if you misspell the word?
What if you misspell it?
Huh?
Well, how would you do that?
What if you put fluoride as an FLUORID?
I know, it gets confusing, doesn't it? Well, this is practice on how to spell them. This is called naming molecular compounds. All right, so what's our name going to be here?
Dinitrogen.
Dinitrogen, our first word. How many oxygens?
Tri.
3. So that's trioxide. This one looks really strange, yes. But it's simple, just like no was. What's our first word?
Nitrogen.
Just nitrogen. We have 1 sulfur. What do we call that? Monosulfide. And to go backwards here. For this guy, you're given a name and you write a formula. Now you can't do supers and subs, so you have to just put it all on the same line. But if you need parentheses, make sure you put those in too, okay? So what is this? Sulfur, that's an S, right? Tetra, that's a 4. And bromide, that's Br. So we have S, Br, 4. One more. Sodium phosphate. Sodium is in A, right? Phosphate, PO4. What's the charge on phosphate? You'll know it in 2 weeks, but it's minus 3. Okay? So, if phosphate's a minus 3, how many sodiums do we have? 3, because sodium is a +1. So you write it, sodium, 3, phosphate. All right, let's stop naming for a minute and let's look at some pretty pictures. We talked about 2 types of compounds. We said that we had covalent and we had ionic. Again, with a covalent bond, we share electrons. With ionic compounds, we completely transfer an electron from one to the other. So electron goes from sodium to the chlorine. Okay? However, sharing in a covalent bond is not always equal. Now let's just look at 2 simple examples here. This is hydrogen, H2. And this represents hydrogen fluoride, HF. Now they both have covalent bonds. In chemistry, we can calculate the charge distribution in a molecule, and we can show it using what's called an electrostatic potential map. Electrostatic potential map is kind of like electron density. It really isn't, but it's kind of like it. And typically we'll take a map and we'll color it to indicate charges. So let's start with hydrogen. With hydrogen we have 2 identical elements here. If we calculate an electrostatic potential map, this more or less tells us where the electrons are around H2. And then we color it. For hydrogen, the map looks like this. It's a nice little green Easter egg. And what that tells you is that, yeah, these 2 hydrogens really are sharing these electrons. They're sharing them nicely, sharing and caring, okay? We do the same exercise here for hydrogen fluoride. Start off with our HF, calculate our map, and then color it. We wind up with something like this. Now, an electrostatic potential map is colored. Blue represents a deficiency in electrons. Red represents excess electrons. So as you look at this covalent bond here, what this is telling you is that the fluorine is being a real hog. It's attracting all the electrons towards itself and leaving none for the poor hydrogen. This is called a polar covalent bond. We show a polar covalent bond with an arrow, and we cross one end. That's the positive end of the dipole, and this points at the negative end. All this tells us is that in this compound, the fluorine is sucking all the electrons down towards itself. Now this concept's going to be very important to us when we do acids and when we talk about solutions, water specifically. So we're just introducing the concept here. This is called a polar covalent bond. Why does this happen? It's something called electronegativity. And you don't need to really understand what electronegativity is. Simply, electronegativity is a scale that goes from 0.7 is the lowest, 4 is the highest. The bigger the number, the stronger it sucks the electrons towards it. Hydrogen here is 2.2, fluorine was 4, and that's why fluorine moves the electron in the covalent bond towards itself. Once again, when we deal with water and when we deal with acids, we'll see that the notion of the polar covalent bond is what causes water to dissolve things and causes acids to become acidic. So just a concept here, any question? Remember, electronegativity simply measures how strongly a given atom attracts the electrons towards itself. All right, let's do a couple very simple problems here. What if you saw this on your exam? Going back to chapter 2-ish. How many protons are there in the sulfur 32 dianion? Well, everybody gets a periodic table. You look and you find sulfur, right? There it is. Let's go ahead and write the atomic symbol. If we were to write the atomic symbol, we would start off just by putting the symbol of the element. That's the S, right? What's the next thing you put on? It's the atomic number, isn't it? Atomic number is 16. And it goes here. And we say this is sulfur 32. What that tells you is that that's the mass number. Mass number goes up top. And then finally, this has a -2 charge. So you would stick the -2 in like that. All right, now answer the question. How many protons are there? It's really just a fancy way of asking. What's the relationship between atomic number and protons? It's the same thing, isn't it? Therefore, there are 16 protons in sulfur 32. And all sulfurs. Number of protons is what defines what the element is.
The -2 you got it from it being in number 7, right?
The what?
The -2.
-2. No, that was given. Again, we know we're in group 6, so it's going to pick up 1, 2 electrons and be a -2. Now we just did naming, so we could do these very, very fast. You know, is what? Nitrogen monoxide. Si is silicon. We have 4 fluorines. What would that be? Silicon, tetra, chloride. 2 phosphorus. So what's it going to be? Phosphorus. And 5 is a pent. And 1 carbon, 2 oxygens. carbon dioxide. These are all polyatomics. Let's just practice those. You can look at your table if you want. SO4, we all know what that is now, right? That's sulfate. CS is cesium. No multipliers, so it's cesium sulfate. What was Cn minus? Cyanide, right? Magnesium's the cation. Magnesium cyanide. NO3, that's the parent of the nitrogens, so it's a nitrate. K is potassium. PO4 is phosphate, that's the parent. This is one less oxygen, so what are we going to call it? Phosphite. Calcium is our cation, so we have calcium phosphite. And our last one here, sulfate we said was SO4, what's SO3? Sulfite. And what all do we have here? We have a sodium, we have a hydrogen, and we have the sulfite. So what do we call it? Sodium, hydrogen, sulfite. Now I can assure you that the naming that we have to do is not going to be complex. Once again, when you see the sample exam, you'll get a better feel for which of the polyatomics you should know. Again, concentrate just on the parents. Sulfate, phosphate, nitrate, cyanide is always fun. Any questions? Yeah.
On example D, I understand that calcium,
Phosphite.
yeah, phosphate, they cancel out obviously, right? In order to not give it the multipliers.
Yeah, phosphite, remember just like phosphate, phosphite is going to be -3. That's why we need 3 calciums, 2 phosphites.
And phosphites come from
PO4 is, PO4 is the parent. That's phosphate. PO3 is phosphite.
so the extra exponent there doesn't make a difference.
Nope. All right, let's go back to pretty pictures here. When we talked about SF4, and we've seen pictures of methane before, things kind of look like, you know, this. This is PF5. We have a phosphorus in the middle, we have 5 fluorines around it. Again, these would be equatorial, those two we call axial. This is methane. This is ammonia, NH3. Now, there are 3 hydrogens on ammonia, but it's not flat. It's kind of like this little pyramid. What we're going to do is figure out a very simple rule that lets us predict what this geometry is going to be. This is called valence shell electron pair repulsion theory. Big words, but very simple concept. The concept is all covalent bonds, all pairs of electrons are going to repel each other. They're electrons, they're negative, they basically want to get as far apart from each other as they can. So depending upon how many things you have around the center of your molecule, the electrons are going to arrange themselves in different ways to try to get as far away as they can. So, if we have two things, and we're talking from the middle here, the electrons can get as far away as possible if we put one on this side and one on the other. If we put three things, this is 180 degrees, three things, we wind up with 120 degrees. Four things, we get a tetrahedron like that. Five things, this is what we had, oops. Well, I guess I can't stop that. But we can show it again. So for two things, we said we have linear geometry. That means something like BeF2. We have two bonds, two covalent bonds. The two fluorines would be like this, as far apart from each other as they can. If we have three things, like BF3 or BH3 we saw, the boron's going to be in the middle, and bonds are all going to be out at the corners of a regular triangle. Because that way they can get as far apart as they can. With four things, we get tetrahedral geometry. Now, for some reason in kindergarten, they never teach kids what tetrahedra are. And they should, because they're really central to all science. In a tetrahedron, you have these four things arranged, and all the bonds are the same angle, all the distances are the same, and the central atom is just raised up off the bottom a bit. Another way to look at it is this way. It's kind of like a little pyramid with the ball balancing up here. Again, a triangle and linear. So depending upon how many things you have around your atom, that's going to define what your geometry is. So let's see how we do this. What would the structure for ammonia be? Ammonia is NH3. Now we've drawn the Lewis structure for ammonia. We've done that. Nitrogen is here in group 5. It has 5 valence electrons, right? Hydrogen has 1. So we put the nitrogen in the middle, 3 hydrogens around. Nitrogen also has this lone pair of electrons. The electrons that belong to nitrogen originally, 1 electron from each bond, and these two, a total of 5. Every hydrogen contributed 1. So everyone see this is ammonia. Now all you have to do is count how many things are around this nitrogen. Well, we have 3 bonds and 1 unshared pair. So we have 4 things. How do we arrange them then? We put our 4 electron pairs tetrahedral. So they're as far apart from each other as they can be. And that's why nitrogen looks like this little flat pyramid. Because you don't see the electrons, but they're in this space up here. This is called the electron pair geometry. So that counts the electron pairs. The other type of way we refer to geometry is molecular geometry. Molecular geometry is simply where the atoms are. And for this, we would call this trigonal pyramidal. So it's a little triangle at the bottom and looks like a little pyramid. That's why nitrogen looks that way. because it has 4 things around it. Now let's do the same thing here for water. Water, oxygen is group 6, isn't it? 6 valence electrons. Hydrogen, group 1, 1 valence electron. We put them together, and we get this. The 6 electrons from the oxygen, 2, 4, 5, 6, and then 1 electron from each hydrogen. Now we count how many things are around it. 1, 2, 3, 4, my gosh. And water looks like this. So water isn't straight like this because it has these 2 electron pairs. It has electron pair geometry, once again, of tetrahedral. We refer to this as bent. All it really is just one part of the tetrahedron, and these guys you don't see, but they're there. We will see that the fact that water is bent is perhaps the most critical property of water in terms of dissolving things, supporting life, everything. If water was straight, it wouldn't work. Turns out that we can do the tetrahedrals in 3 different ways. If we have 4 bonds, that's a full tetrahedron, just like methane. If we only have 3, like ammonia,